All right, Chemistry 3111. We said we were going to start off when we came back by looking at question 19.8. I guess I got a little happy with my mechanism here, but one thing I wanted to point out to you, okay, and I'm going to draw something and then I'm going to erase it, but it tells you that you have a catalytic, right? This square bracket represents a catalytic amount of sulfuric acid, and then you have excess methanol, okay? So if I combine methanol with sulfuric acid, H2SO4, there's going to be an equilibrium in between this and the protonated form of methanol, right? The conjugate acid of methanol plus the hydrogen sulfate ion, like this, okay? Well, the pK of sulfuric acid is about -9, and the pK of this is going to be close to the pK of hydronium, which is around -2. So that means the equilibrium is going to lie to this side. So the major acid that you actually have in the reaction mixture is what I have in the red circle, not sulfuric acid. So when you draw the protonation of the first step to form the oxonium, what I have in the red circle, the conjugate acid of methanol, should be the acid that you draw, not sulfuric acid. So I'm going to erase this, okay, and delete, and we're going to start by drawing the conjugate acid of methanol. And just bear with me, there's not a lot of room here to stick all this in here, but let's try and do it. So we have the conjugate acid of methanol. It looks like this. So our first step is going to be a proton transfer, like this, and that is going to give us the oxonium ion, which is going to be highly susceptible to nucleophilic attack by our alcohol. So we have our oxonium ion, like that. Now we went from a good electrophile to an amazing electrophile, a very, very powerful electrophile. So the next step is going to be for our methanol. Remember, it's not all protonated. This is just a catalytic amount of acid, okay? So now the methanol is going to come in as a nucleophile. So we're going to do a nucleophilic attack. We can't have 5 bonds to carbon. And so we have to break the pi bond. And so that's going to give us our 5-membered ring. We're going to have our hydroxyl group. We're going to have our oxygen with a hydrogen and our methyl group on it. So it's got a positive charge, okay? But before we can get to our hemiacetal, another equivalent of methanol has to come in. Remember, there's lots of methanol, okay, to abstract this proton, and then we will have our hemiacetal, okay? So at this point, we'll have our hemiacetal. So we have our hydroxyl, and we have our methoxy group on here. So this is the hemiacetal, like that. Now, in the second half of the reaction, remember that we lose water. So that means we're going to lose this, but we can't just fly away. It's got to be protonated first to convert it into a good leaving group. So we're going to do a proton transfer. So we'll draw our major acid, which is going to be our protonated form of methanol. So we'll draw that, or the conjugate acid of methanol, whatever you want to call it. So we're going to get a proton transfer to convert the hydroxyl into a good leaving group. So we end up with something that looks like this. So we have our protonated hydroxyl group. So that's going to be a good leaving group. Then we have our methoxy here. Now, we can't just draw this leaving like that, okay? We can't do that. What we have to do is we have to form a new pi bond here, and then we can lose the water. So this is the step where we lose the water. So we can put here negative H2O. So this is where we lose water. And now we're going to end up with this oxonium, but instead of a hydrogen, now we've got a methyl group on there. Okay, so now we're going to have another equivalent of methanol come in there as a nucleophile. So we'll write methanol. It's a good nucleophile. This is an excellent electrophile. We have to break the pi bond, and that is going to get us one step away from the final product. So now we've got a methoxy group here, and we have a methoxy group here, okay, which is protonated, like that. And then to do the last step, oops, where's my black pen? The very last step is just going to be a proton transfer. So we're going to have methanol, which is going to grab that proton, and we regenerate our uncharged species like that. So those are the 7 steps for the formation of an acetal. And I highly recommend that you try this until you can do it. Okay, very important mechanism, the formation of an acetal. Now that we have that done, let's take a look at these syntheses here. So the first one is just adding 2 carbons at the end of this terminal alkyne, but keep in mind that we have a ketone in there. And so if you were to treat this with sodium amide, right, amide is a good nucleophile, so it's just going to go in here and ruin your carbonyl. So that means the first thing you have to do is protect that carbonyl. So we'll convert it into an acetal. So let's see here. What's our first step going to be? Our first step is going to be to convert it into an acetal. So we need ethylene glycol, right? To make our acetal, we need a catalytic amount of acid, and we always write negative H2O. That means we're losing water. And so at that point, you would have this. You would have this intermediate where you have the cyclic acetal, then you would have your terminal alkyne like this. So the next couple of steps are just going to be chapter 9 chemistry, where we're going to treat it with sodium amide. Okay, then we're going to treat it with ethyl iodide. Okay, and that would install the ethyl group. So now we would have the ethyl group like this. And then to remove the acetal, what we use is H3O+. Okay, so just aqueous acid removes the acetal. So this would be an intermediate along the way. Okay, so anyhow, there you go. So those are the steps for that one. The next one is in the same vein. We're going to have to take this ester and react it with a Grignard, phenylmagnesium bromide twice. But remember, phenylmagnesium bromide, right, it's also going to react here, so we have to protect the ketone as an acetal. So let's start by doing that. So remember, it only works with aldehydes and ketones, so we're going to have our ethylene glycol, a catalytic amount of acid, and we're going to lose water in the process. And so we're going to have our cyclic acetal, which is going to look something like that. Then we've got our ester over here. So then the next thing we're going to do is we're going to do the Grignard chemistry. So we're going to use excess phenyl magnesium bromide, and then followed by aqueous acid. Okay, and remember, the aqueous acid is not only going to protonate here, but it's also going to remove the acetal. So it's going to do two steps in one, and that's going to take us all the way up to, maybe I should use a black pen. It's going to take us all the way up to our final product, just like that. So it's a 3-step process overall. There you go. So a little bit of synthesis that involves acetals, and then the mechanism for the whole formation of an acetal. Very important stuff. So let's switch gears and talk about not oxygen as a nucleophile. So we're going to turn away from acetals and hemiacetals and hydrates for a second, and we're going to start by talking about nitrogen as a nucleophile, namely primary amines. And primary amines, when we take a primary amine with a catalytic amount of acid and we remove water and we react it with an aldehyde or a ketone, we end up forming an imine. And an imine, if you Google imine, they used to be called Schiff bases. So Schiff base. Okay, it was named after Hugo Schiff, who was the guy who developed them. But anyhow, so you form an imine, and an imine is a new functional group. So an imine is nothing more than this. So you have a nitrogen and you have some kind of R group here. Okay, the R group can even here. This R group could even be a proton, and it's still called an imine or a Schiff base. So again, a primary amine with an aldehyde or a ketone, catalytic amount of acid, remove water, gives you an imine. Now, the book goes into quite a bit of detail about the mechanism of this reaction. I don't really quiz my students on the mechanism of this one. I'm more concerned with you knowing the mechanism of acetal formation. And this is very similar. You'll see that there's 3 steps to form an intermediate. Instead of a hemiacetal, this time it's called a carbonylamine. Then you have the last 4 steps with a loss of water. that gives you the imine. So there are a lot of similarities. But if you take a look at it, the first step is not protonation of the oxygen of the carbonyl. Rather, it's a nucleophilic attack by the amine. And then you end up with something that's neutral, right? You have a negative charge on the oxygen, but you have a positive charge on your nitrogen. So then you have a proton transfer followed by another proton transfer to give you this intermediate called a carbonylamine. You should know what a carbonylamine is, okay, what the structure is. It's a carbon, okay, that has two R groups. You have a hydroxyl group on one, and then you have an amine on the other. Okay, that's what a carbonylamine is. Then you do another proton transfer to convert the hydroxyl into a good leaving group. A loss of water is your leaving group, then another proton transfer, and you get the imine. Again, I don't really bother my students with this mechanism a whole lot. The main thing is that you know what the reaction is. However, if you're a student, and I know you all are, you probably noticed, well, you're in acid and your first step is a nucleophilic attack. Well, that is true. And the reason why is you can't, even though the reaction is an acid, it's a catalytic amount of acid. You can't protonate all the amines with strong acid, otherwise there'd be nothing left over to do the nucleophilic attack here, okay? So again, like it says here, even though you're under a strongly acidic conditions, if you had too much acid, all you would end up with is ammonium ions, okay? And so, yes, the ammonium ion is the acid catalyst for this, but it says here that the ammonium ion is not acidic enough to protonate the aldehyde or a ketone, but it is acidic enough to transfer a proton to the negatively charged oxygen. So again, even though the ammonium ion can't protonate this, it can protonate that because that's got a negative charge. Now, am I going to ask you to write an essay about this page or anything? No, but it is good food for thought, and you should, by now, you should understand if you take an amine and put it with a strong acid like HCl, the equilibrium is going to lie completely to this side. So this is the acid catalyst, okay? It's not like you've got sulfuric acid floating around in there. You don't. You've only got this ammonium ion, which is your acid in there. And so because of that, the pH has to be just right. It's got to be right around a pH of 4.5 to 5, something like that. Because at a lower pH, if it's too acidic, all of the amines are protonated. There's going to be nothing left over to attack the carbonyl. And if you're at too high a pH, if it's too basic, then you've got no acid catalyst around. So to form an imine, you have to have the pH being just right, okay? It has to be just around a pH of 5 to do that. So what if you have a ketone and instead of an aldehyde, you have a secondary amine, okay? So if you have an aldehyde or a ketone and you have a secondary amine instead of a primary amine, well, in that case, we don't get an imine. We form what's called an enamine, okay? So we form an enamine from a secondary amine. So you can see here we have a secondary amine, catalytic amount of acid. We lose water, and you guys have to know what an enamine is. So an enamine is a new functional group. Learned a bunch of new functional groups. So you have an alkene with a nitrogen and two R groups attached to it. This is an enamine, like that. So I thought I had something written in my notes here. So where was it? Oh yeah, it's right here. So I'll show you in a second. Anyhow, it says the reaction requires acidic conditions. The mechanism is identical to this one, okay? This one, enamine also, except for the last step, except for last step. The last step is different, and the reason why is because a secondary amine doesn't have a proton here to do the proton transfer at the end. Okay, so what do we do instead? Is that all of these steps are identical. Here, all of this is the same. The only difference is the very last step. Okay, it's this step here. Since you have two R groups on here because you have a secondary amine, what do is you look at the adjacent carbons, the ones next to the carbon involved in the double bond, and you take one of the protons off of it, and you form your double bond to make your enamine, like that. So, in summary, if you have a primary amine, you form an imine. If you have a secondary amine, you form an enamine. And this is, I have it written down here. The mnemonic that my students gave me years ago is this. For a primary amine, so number one, they said imine. Okay, the number one kind of looks like the letter I. And then for an enamine, they put for a secondary amine, they put here, kind of looks like the letter E. So enamine. Okay, so secondary and primary. I don't know if that'll help you. Maybe yeah, maybe no. Depends on the person, probably. Son of a gun, did I unplug that? No. Okay. There we go. So imines and enamines. Remember, an imine is also referred to as a Schiff base. That's the old way we name them, but it's still considered a proper way to name an imine today. So now that we've covered that, this interesting compound here, okay, NH2NH2, I don't think you would have learned this in general chemistry, but I'll scribble it down up here. If you have NH2, NH2, this compound is called hydrazine. So if you use hydrazine as your primary amine to make your imine, now you end up with this cool intermediate over here, and this is called a hydrazone. Highway to the Hydrazone, right? It's a song by Kenny Loggins. Anyhow, so this is your hydrazone here. And if you're wondering, well, what the heck are you teaching me this for? Okay, it's because you can take the hydrazone and you can do this reaction here. This is called a Wolff-Kishner reduction, and that is going to convert the hydrazone. It's going to reduce it to a methylene, right? You have a CH2 group. So, and if you're looking at this and going, wait a second, this is the same thing as the Clemmensen reduction, okay? You had zinc and the mercury amalgam, HCl, and heat, and you also said that was a way to reduce a carbonyl. I'd say you're absolutely correct. Okay, absolutely. These are both perfectly reasonable ways to reduce a carbonyl all the way down to a methylene group. But this is just a different way of doing it. And I don't test my students on the mechanism of the Wolff-Kishner, so you don't have to know this mechanism. However, I will show you the coolest part of it. And the coolest part is, you see it's a series of proton transfers, but there's a loss of leaving group in here. And what is the leaving group that's lost? If you follow the curved arrows here, the leaving group that's lost is nitrogen gas, right? This is a negative. So you end up losing nitrogen gas. Well, where does that go? Up the smokestack, right? It goes out into the environment. And so that is what drives the reaction forward, is the loss of nitrogen, which is a gas. Okay, so based off the Chatelier's principle, Wolff-Kishner reduction is a great reaction because once the nitrogen is gone, it's not coming back. It pushes the reaction forward. So there you go. So note the many similarities that we've seen between these acid catalyzed mechanisms. Remember, under acidic conditions, everything should either be neutral or have a +1 charge. If you are practicing your mechanisms at home and you end up with something that has a -1 charge and you're in acidic condition, there's something wrong. Something seriously wrong happened along the way. Okay? So with that in mind, there's question 19.15, 19.17, 19.20, 19.7, which deals with hydrolysis of acetal, so we're going to cover that, and then hydrolysis of imines and enamines, and then there's some more hydrolysis questions here. And then I wanted to save the section on sulfur nucleophiles. So I don't want to solve every single one of these problems with you today because I'd like you to try them at home, but I'll kind of walk you through one of each of them, okay? So if we start with 19.15, it just says predict the major product, okay? We're not asked to draw a mechanism. Well, here we have a ketone, okay? And this isn't a primary amine, this is ammonia, okay? So we're using ammonia, which certainly isn't a secondary amine. It's like a primary amine in a way, except your R group is nothing but a hydrogen atom. So what is that going to give us? Well, it's going to give us a Schiff base, isn't it? An imine. So let's draw our 7-membered ring. Now we're going to have a double bond in our nitrogen, but instead of an R group up here, our R group, since it's ammonia, is going to be a hydrogen, like that. So this means we formed our imine. Now in the second one, we have another primary amine. So I'd like you guys to give this one a try before class on June 5th. Okay, I want you to try this one. So again, this is a ketone. We have a primary amine, so we're going to form an imine again. I want you to try to draw that imine. In the next one, we have hydrazine in the second one, 19.17b. But in the first one, if you have this molecule, OH, NH2, this is called hydroxylamine, and it's like a primary amine, right? It's like as if this was an R group. And so you can imagine that if you react it with this 3-pentanone, you have your double bond, your nitrogen, but your R group now is going to be an oxygen like this. And this actually is a new functional group. This is called an oxime or an oxime, depending on who you're talking to. And the reason that you learn what an oxime is because oximes can be used to make heterocycles, like this one here. I don't know if this one showed up in our chapter on aromatic compounds, but you can see that this is an aromatic compound. And this is called isoxazole. Come on, you isoxazole. Okay, so that's what you would use, or one of the reasons you could use an oxime is to make an isoxazole. So the next one down here, you have hydrazine, and you have a ketone. And so I want you to draw the hydrazone that would be formed, and we'll do that in the next class. So I want you to try to draw that hydrazone. The next one, it says predict the product. And now in this one, we have a secondary amine and we have a ketone. And so we're not going to form an imine, we're going to form an enamine. So what's our enamine going to be like? Well, let's draw the ketone. Okay, so here's our ketone. I'll show you how I would do it, okay? Here is our secondary amine, okay, like this. So what you have to do is remember that you're going to lose all of this, okay? And the double bond is going to be like this, but it can't be a double bond because you don't have two hydrogens. So you can erase one of these and you end up with your enamine like that. Okay, it's kind of a goofy way of showing you, but hopefully somebody who's hearing the sound of my voice will hear it and find it helpful. So here's what we're going to do. We're going to draw the 5-membered ring from our carbonyl, but now instead of being attached to the oxygen, it's going to be attached to the nitrogen, which they both still have those big cyclohexyl groups on them. So there's a cyclohexyl group here, there's one here, but now the double bond is going to be here on that carbon that is attached to the nitrogen. So this is an enamine. An enamine. Now the next one is more challenging because you have your secondary amine in a chain, and you have your ketone as part of that chain. So you're going to form a ring. Okay, you're going to form a ring, and there's going to be 1, 2, 3, 4, 5 atoms in that ring. So I want you to try to draw that ring that is formed, and it's going to be an enamine. Okay, and we're going to try to draw that on our next class. Okay, so that brings me to the hydrolysis of an acetal. And we actually talked about this one already. We said that if you took your acetal and just put it in H3O+, remember when you combine water and aqueous acid, a catalytic amount of acid, you get H3O+. So if you take your acetal and put it in aqueous acid, it just blows it apart right back to your carbonyl, whether it's an aldehyde or a ketone. It gives you your alcohol, whatever. Again, but one thing that's important to note is that acetals are very strong under basic conditions, okay? If you're in base, so you can see sodium hydroxide is an extremely strong base. They don't react with a strong base whatsoever. So that's why they do make good protecting groups, because they're so tough. Now, the mechanism of this reaction is going to be identical to the mechanism for this reaction, but in reverse. Right? It's going to be identical to the mechanism that we saw for the formation of an acetal from a ketone and alcohol with the removal of water. It's just in reverse. So this mechanism, that we're on page 59, is the exact same mechanism as the one on page, where was it? I've got to go back quite a ways. No, keep going. 59 and, well, I guess that's it there, but go all the way back here. Where was it? Come on. So 59, it's the same one as on page 35. Okay, it's the exact same mechanism. So we'll say here, reverse of page 35. It's the exact same mechanism, just all the arrows are drawn backwards. That's all. You can follow it, try it. It'll the exact same thing. And that's based off of something called the principle of microscopic reversibility. What that means is if you draw your curved arrows in one direction going one way, all you have to do is flip them around to do the opposite. Okay? It's not like it's never some new mechanism or anything like that. So that's why I'm not going to go over this mechanism in dirty detail, because it's the reverse of the mechanism on page 35. I recommend trying it and understanding why, if you're an acid, you notice that there's no negative charges in any of the intermediates along the way. But we know how to hydrolyze an acetal. And even though the mechanisms of these aren't shown in the textbook, and I won't ask you to draw them, it turns out that the mechanism for the hydrolysis of an imine, come on, pen, an imine or an enamine, okay, the hydrolysis is the same thing. You just combine them with aqueous acid. So remember, you put these together, you get aqueous acid, and it just goes all the way back to your ketone, okay? Again, the mechanisms of these reactions, okay, both of these reactions are not shown directly in the textbook, but remember, they're just the reverse of the mechanisms of their formation, which are already covered in the textbook in gross and gory detail. So what we're going to do now is we're going to look at some hydrolysis of, here we have an acetal, here we have an imine or a Schiff base, here we have another acetal, and this is an enamine. So let's try the first couple. Okay, you can see that this is clearly an acetal because you have your carbon, oxygen, carbon, carbon, oxygen, carbon. So there's your acetal. So if I put it in aqueous acid and I hydrolyze that, what am I going to get? I'm going to have my 5-membered ring, but instead of being attached to 2 oxygens through 2 single bonds, it's going to be attached to 1 oxygen through a double bond. And then my alcohol is going to be this, the 1, 2, 3 carbons. So it's going to be this diol. So it's going to be 1,3-propane diol. Now here's my imine, my Schiff base. So I'm going to break this bond right here. And so my starting ketone is going to look like this. We're going to have a double bond, but not to nitrogen, but rather to an oxygen atom. In my primary amine, it's going to have a nitrogen with 1 methyl group, so it's just going to be methylamine. There you go. So what I'd like you to do for next class is I'd like you to try to draw this, the products of these 2 reactions, 19.23 C and D, and that brings me to the section on sulfur nucleophiles. So I can cover this with you pretty quickly because ketones and aldehydes, look at this, react with thiols virtually the same way that they do react with alcohols, right? So you guys know that this is called a thiol, right? It's just the sulfur analog of an alcohol. So if we take our aldehyde or ketone and treat it with 2 equivalents of a thiol, instead of an acetal, we get a thioacetal. If you use 1,2-ethane dithiol, this compound here, you end up with a cyclic thioacetal. Now you might be wondering, okay, well, what's the difference between an acetal, which was this, right? What's the difference between an acetal and a thioacetal? It's a good question. And the answer is sulfur can behave quite a bit differently than oxygen in some ways. And so there's something called Raney nickel. It's a reagent called Raney nickel, which can be used to reduce the thioacetal all the way down to an alkane, okay? It's actually a pretty dangerous compound to work with, Raney nickel. It's pyrophoric, meaning it can just ignite in the air. But anyhow, Raney nickel will reduce your thioacetal down to an alkane. So what does that mean? Now you can take a ketone and you can reduce it down to an alkane using the formation of a thioacetal followed by treatment with Raney nickel. Now there's no mechanism No mechanism for this in our textbook whatsoever. It's way beyond the scope of our class, so don't worry about a mechanism for Raney nickel. But now you might be looking at it. Where was it? I thought I had it in here, but I guess I don't. You might be looking at this reaction here, okay, and saying, well, now I've got three ways of doing this. I can do it with the Raney nickel. I can do it with a Clemenson reduction. Clemenson, okay, you can write out the conditions with zinc, mercury, amalgam, hydrochloric acid and heat. And I can also do it with a Wolff-Kishner reduction, right? I can form the hydrazone and then do a Wolff-Kishner reduction. So now we have three ways of doing the exact same thing. Now, before you throw something at me and say, why do I have to learn three ways of doing the same thing? Well, like I told you before, all good organic chemists, she or he should be able to look at a reaction and say, well, I could try this and this and this, because it's going to be substrate specific. Maybe you try the reaction, maybe you try the Clemenson and it gets you like a 10% yield, but then you try Wolff-Kishner and it gives you a 70% yield, and then you try Raney nickel, that pathway, and it gives you 95. Well, you're going to go with the one that gives you the higher yield, right? So you have to try, since you're usually pushing the frontiers of science, you want to try all the different possibilities and pick the best one. So what we'll do right now is we'll take a look at this first question, 19.26a. So in the first step, what we're going to do is we're reacting with the 1,2-ethane dithiol in a catalytic amount of acid. So that's going to give us the thioacetal, which is going to look a little something like this. I think my Apple Pencil is tired or something. Okay, so that's after the first step. And then after treatment with Raney nickel, it's just going to reduce it to the alkane. So we end up with the alkane like that. And so what we're going to do with the second question is we're going to save this for class on Wednesday. And what we'll do on Wednesday is, after we try those practice problems that I just highlighted, we'll start with a little bit of review, because we've already talked about lithium aluminum hydride and sodium borohydride in detail. So we talk about that for a little bit. Then we talk about Greenyard, which again is nothing new to you. So a little bit of review for the beginning of next class. So that's kind of cool. Then all we have left to cover is what's called a cyanohydrin. So we'll talk about the formation of a cyanohydrin in acid and in base. Then after that, we cover the Wittig reaction. And remember, Wittig, if you read ahead, is an extremely important reaction in organic chemistry, just like a Greenyard. It's a Nobel Prize winner. After the Wittig, so the Wittig takes a little while to get through. And after that, we cover the last reaction in the entire chapter. Let me find it. Come on, Mr. Dion, which is the Baeyer-Villiger oxidation reaction, okay? And the Baeyer-Villiger will be the last one. So if we go down to the very end, okay, you can see what we've covered today. Let me just erase some of this spinach here. So what we covered today is we covered, come on, pen, we covered the formation of a hydrate, an acetal, a cyclic acetal, a thioacetal, Raney nickel reduction, the formation of an imine or a Schiff base, an enamine, a hydroxamine, an oxime rather, a hydrazone. We covered the Wolff-Kishner reaction. And so what we're going to do next class is going to be this here. But remember, this is going to be a review, the lithium aluminum hydride. The Greenyard will be a review. So all we'll really have that's going to be brand new will be the cyanohydrin, the Wittig reaction, and the Baeyer-Villiger reaction. Those will be the last things that we'll look at that will be brand new in this chapter. So we covered the majority of the chapter today. And so after we finish those last few reactions, we'll do a little bit more practice, either on Wednesday or on Friday, because we have some time allotted to this chapter on Friday. And then on Friday, we'll also start chapter 20.